We've all been to the beach, right? You see the ocean tides, that steady, rhythmic rise and fall of the sea. And you probably think, oh yeah, the moon's gravity pulls the water. Simple. But what if I told you that simple idea hides this absolutely mind-bending cosmic story? A story that involves stretching planets, a celestial tug-of-war, and a moon that is slowly but surely slipping away from us. Let's dive in.
Okay, let's start with the big puzzle, the question that kind of breaks the simple explanation. We get a high tide when the moon is right overhead. That makes total sense, right? Moon pulls water. But there's another high tide on the complete opposite side of the planet at the exact same time. How does that work? If the moon is pulling the water towards it, shouldn't the far side have the lowest water level, not a second high tide? Solving this one is the key to everything.
So, just to set the stage here, our planet gets this double high tide not every 24 hours on the dot, but every 24 hours in about 50 minutes. The real mystery is, why two? Why these two bulges of water on opposite ends of the globe?
You know, the explanation you always hear is that the moon's gravity just kinda lifts up the water on the side facing it, and boom, there's your bulge. And yeah, that's true, but it's only half the story. It's an incomplete picture, because it does nothing to explain that second bulge. The real answer is so much cooler, and it has less to do with lifting, and a whole lot more to do with stretching.
This is it. The key to unlocking this whole thing isn't thinking of gravity as a simple pull. It's a differential force. It's a stretch.
First thing to get our heads around, the moon's gravity isn't just pulling on the oceans. No way. It's pulling on everything. The water, sure, but also the continents, the molten core. It's pulling on the entire planet. And here is the absolute crucial piece of the puzzle. That pull isn't the same everywhere. Since gravity gets weaker with distance, the moon pulls hardest on the side of the Earth that's facing it. It pulls a little less on the center of the Earth, and it pulls weakest of all on the far side of the Earth. This difference is what changes everything.
So this difference in gravitational pull from one side of our planet to the other has a name. It's called the differential tidal force. And its job isn't to lift the Earth, it's to stretch it out, to elongate it, kind of like turning a basketball into a slight football shape.
And here's how that stretch perfectly solves our mystery. On the side near the moon, the water is pulled away from the Earth's center more strongly than the Earth itself is. That's our first high tide. But check this out. On the far side, the solid Earth itself is actually pulled away from the water, which is feeling the weakest pull. The water is basically left behind, creating that second equal high tide. And just like that, the mystery is solved. We have our two tidal bulges. Okay, so now that we get how the moon does this stretching thing, we can bring in the other big gravitational player in our solar system, the sun. Because yeah, it gets in on the action too, adding a whole new rhythm to this celestial dance.
Now, this brings up a really good question. The sun is gigantic. It's 27 million times more massive than our little moon. Its total gravitational pull on us is way, way stronger. So why doesn't it create these enormous, colossal tides that completely dwarf the moon's?
Well, the answer goes right back to that differential force, that stretch. Remember, tides are caused by the difference in gravity across the Earth. And that stretching effect gets a lot weaker over long distances. So even though the sun is a beast, it's so far away that its tidal stretching force on us is only about 44% as strong as the moon's.
But the sun's effect is still a big deal, especially when it decides to team up with the moon. When the sun, earth, and moon are all lined up, during a new moon or a full moon, their stretching forces add together. This gives us extra high tides and extra low tides, which we call spring tides. But when the sun and moon are at a right angle to us, their forces kind of fight each other, leading to much weaker, less extreme tides. We call those neap tides.
Now, this constant stretching isn't just about moving water around. Over billions of years, it has some really profound effects on the whole Earth-Moon system. It's like a slow-motion cosmic tug-of-war, and it's been going on for a very, very long time.
So here's the setup for the battle. The Earth spins on its axis once a day. The moon, on the other hand, takes about a month to go around us. This means our planet is rotating through these two tidal bulges of water, and that creates an unbelievable amount of friction as trillions of tons of water slosh against the ocean floor.
And all that friction has this really fascinating result. It actually drags the tidal bulges a little bit forward, so they end up slightly ahead of the moon in its orbit. The moon's gravity then pulls back on this watery bulge that's gotten ahead of it, and this constant, gentle pullback acts like a brake on our planet's spin. The whole process is called tidal braking.
And believe it or not, we can measure this. Because of this tidal braking, the length of an Earth day is getting longer by about 0.0016 seconds every single century. Now, that doesn't sound like much, but over geological time, it's a huge, huge change.
So this brings up a pretty important question, right? All that rotational energy the Earth is losing, it can't just vanish. Energy has to go somewhere. So where does it go? Well, it turns out it gets transferred directly to the Moon.
It's one of those fundamental laws of physics, the conservation of angular momentum. In a closed system like the Earth and Moon, the momentum lost by the spinning Earth has to be gained by the orbiting Moon. There's just nowhere else for that energy to go.
The easiest way to think about it is like this. As the Earth's spin slows down, it's giving the Moon a constant, tiny push forward in its orbit. That little energy boost kicks the Moon into a slightly higher and more distant orbit. So the Earth slows down, and in exchange, the Moon drifts away.
And we can measure this with incredible precision, using lasers that we bounce off reflectors that the Apollo astronauts left on the Moon. We know for a fact that the Moon is moving away from the Earth at a rate of about 4 centimeters every year.
4 centimeters a year, it probably doesn't sound like a lot. But to put that into perspective, that's about the same speed that your own fingernails grow. Just think about that. A slow, steady, cosmic escape happening right now at the pace of a manicure.
So let's just quickly recap this incredible story. We started with a simple question about why there are 2 high tides, and we ended up on this journey through differential gravity, planetary friction, and the laws of physics. That gentle rise and fall of the sea that we see is actually the visible proof that our planet's spin is slowing down and our Moon is slowly drifting away into space.
And that leaves us with one last thing to think about. This process isn't stopping. Billions of years from now, the Moon will be much, much farther away. It'll look smaller in our sky. Days here on Earth will be much longer. So, what does that future even look like? It's a pretty cool reminder that even the things we think are constant, like the length of a day, are really just part of a grand, evolving cosmic story.